Okay, let's look at static equilibriums. So if you look at the word static, static means something is not moving. Now, and equilibrium means that something is inequality, okay? So in the case of a static equilibrium, what is inequality is all the forces. There are kinetic equilibriums as well, and we did an example of that yesterday. So for example, yesterday we did an example of a helicopter flying along, okay? This thing is moving, and yet if everything else is constant about it, so if lift and gravity and forward force from the rotors and engine and drag from the air all sum to zero, they sum to zero, we're in an equilibrium, but it's a kinetic equilibrium, okay? So what we're interested in is we want to talk about things that are in static equilibrium, so not moving at all. The very simplest example of a static equilibrium probably would just be something like if this, whoops, this represents a tabletop. Oh, I wonder if I can change its, there we go. If this represents something sitting on a tabletop, and it looks like this. Okay, so we have a box sitting on a tabletop. How do I change it to color? I want it to be a different color. I want it to be green. All right. If we were to examine the forces acting on this object, it's not a good color. Find a good color. There we go. We've got the force of gravity working downward. Now we've got an equal and opposite normal force pointing up. Okay. This is an equilibrium because the normal force and the gravitational force are equal and opposite. And if we were to sum them, okay, and we were to look, you would find that if you redrew these tip to tail, you know, you'd get Fn plus Fg going down, and from start to finish gives you a net of zero. Okay, so that's the basic concept behind this. That's what we're talking about. So the first kind of static equilibrium that I think we'll talk about is if instead of having something sitting on a surface, you instead have it hanging from, say, the ceiling. And a good example of something like that might be, say, what just happened there? If we were to, I don't know, put a flower in a flower pot, hang it from the ceiling. Right. I don't see too many hanging plants anymore, but let's say you did have a hanging plant. What you have going on here is you have force of gravity. Wow, what the heck? The force of gravity aiming down. Right? And then you have a tension, which is basically a pulling force in a cable or a rope, aiming upwards. Okay? So we call this the force of tension, and this the force of gravity. All right? So let's say you were given a problem with a simple scenario like this, and it says calculate the tension in the cable if the plant weighs 4 kilograms. Plant and pot weighs 4 kilograms. So how do you figure this out? Well, you know, based on the fact that that plant isn't moving, that the net force on here has to be 0, right? So then you would say that since F net, the net force, is equal to the sum of all the forces acting on here. Oops. That's not how we do sum. Sum is plus. Okay, and we also know that the net force equals 0. What we can sort of derive out of here is that these two forces have to be equal and opposite to each other. Okay? This negative sign just indicates the direction that the forces are acting in. All right? If you remember, we calculate the force of gravity is equal to the mass of the object multiplied by the acceleration due to gravity. This is just a special case or a standard case almost of Newton's second law. F, any force, is equal to the mass times the acceleration. There's a constant acceleration in Earth's gravitational field, at least close to the surface of the Earth, of negative 9.8 meters per second squared. So what this is going to work out to, if we want to know what the tension is, we simply have to rewrite this to solve for that, right? So your tension is going to be equal to the negative of Fg, or negative mg. And what that is going to be is, if we have a 4 kilogram plant, and we have a negative 9.8 meters per second squared acting on it, and let's not forget that there was a negative in front of the whole thing, what you'll end up with is 39.2 newtons. Okay? So there's roughly about the simplest case. The same thing would apply if this plant were sitting on a tabletop and they asked you to find the normal force, right? It's exactly the same scenario. It's just now we're referring to a tension force. So tension is just the pulling force in a rope or a cable, right? And it acts in the opposite direction to gravity. Are there any questions about that? Okay, so here's a slightly more advanced scenario. I just forgot to hit record. So essentially what we have is we have a mass hanging from the ceiling. We're not really interested in the tension here. It's going to be just like the previous example. We've given these angles of 40 degrees. And what we're interested in is now solving for what the tension will be here. Now, you might think right off the bat, oh, the tension will be exactly the same as the tension in here. That's not actually true, right? Think about if these were on like adjustable sliders, say, right? And let's say we start to slide this farther outward this way, okay? As you do that, what do you think is going to start happening to the tensions as we go out farther this way? Or, if you want, as we decrease the angles here? What will happen to these tension values? They'll increase, good, and that's logically what we would expect, okay? Here's another question. If this is done with a cable, right, could I ever pull these so far that this angle becomes 0? It's just a normal cable. I mean, like a clothesline cable or something. You think it would break before you could get to an angle of 0? Okay, keep that question in mind, because I think you'll be able to answer it better after we're done. So, how are we going to go about doing this? Well, the first thing I think that we need to do is we need to start to split this up. Now you see we're dealing with forces at angles, much like we dealt with velocities and other things at angles. So there's going to be components to this. So the component system is going to come back here, and we're going to have to use it. And let's just see here what we want to do. I want this, and I want it to look like this. And let's see if that will give me what I want. Oh, nice. Okay, so we have that, all right? And we have this, and we have this. Okay, so what are those things? Well, if we think about it, okay, and you know what I'm going to actually do? This is maybe technically a good place to visualize this, but it's going to make our math a little harder. So I'm going to actually just move this over here. Okay, I'm going to pull this down just a bit. I'm going to pull this down just a bit. Okay, and I'm going to pull it right down to here. I'm going to pull this right down to here. Okay, and I want you to just kind of realize that we sort of have some solvable things here now. Okay, so let's start to label what we know about this stuff. So let's look at tension 1. Okay, so we've got the tension you can probably see is acting, if we look at this just individually, upward and to the right. Okay, as we have with the arrow, it's got to be upward and to the right. And can I just move this out of the way too? Go out of the way here. Okay. So we have, this is the x-plane, right? We have, oh, why is that so ugly now? Okay. Jeez. Color problems here. Okay, so we're going to call this T1x. We know that it's in this direction. Okay, and then we've got T2x. So this is the x component of T2, and it's got to point this way. Okay. Then we start to look at the second scenario, right? We have our force of gravity aiming down here, and we know that Fg is equal to mg, right? And that's in the downward direction. And we also have T1y here and T2y here, aiming upwards. Okay? Now let's write out a couple of equations that talk about what's happening here. I think probably what you'll notice is that T1x has to be exactly equal to T2x, but in opposite directions. Okay? So if we say F net x is equal to T1x plus T2x, and we know that F net x has to be equal to 0. It's not moving side to side. It's not accelerating side to side. Then same logic as before. Kind of doing this the long form here, but we rearrange this. The magnitudes of those two are going to be equal, but they're going to point in opposite directions. They're going to cancel out. We're going to have 0 net force in the x direction. Okay? The other thing that we see is we have T1y and T2y and mg all in the y direction, right? Well, we also know that F net, the net force in the y direction, equals 0. It's not accelerating up and down either. So at the addition of all these y forces equals 0 as well. So if we get F net in the y as being equal to mg plus T1y plus T2y, you with me? Extend the page. Then using the same concept here, if this is equal to 0, we should be able to say that T1y plus T2y together equal the opposite of mg. Okay, so something that I want you to notice here, if we look at this, okay, we've essentially proven that T1x and T2x have to be equal in magnitude. We also know that these two angles are equal, right? And geometry-wise, if these two lines are parallel, then this angle in here and this angle in here are also equal, right? So we have equal sides and equal angles. That must mean that the hypotenuse values are equal. In other words, T1x equals, T1 equals T2. Okay, so let's just say that that's the next thing we'll talk about. If all of the above is true, sort of writing a proof here, right? Then we know that the tension 1 has to equal the tension 2, and you know, I guess what we're actually, I shouldn't put a negative sign there. We're not considering direction. And direction's not super relevant, but I guess like you could say they are in opposite directions, sort of. I mean, they're both pointing up. So now how do we go about solving this? And I guess the other thing too to notice here, right, that I guess we have to get around to is that T1y and T2y have to also be equal, right? If T1 and T2 are equal, these are equal and these angles are equal, then T1y has to equal T2y, okay? And since theta 1 equals theta 2, and the reason I'm beleaguering this point a little bit is because eventually we're going to do it where these angles are not equal, they're no longer equal, which would happen, say, if I were to slide this over here, like if this were, say, movable and I slid it over here, now we'd end up with a more acute angle and a more oblique angle here, right? Is that the right word? Less acute, maybe? It wouldn't technically be oblique, it would just be less acute. Anyway, obliquer, acute, less. I'm recording this. I should continue. Okay. Just want to write a real nice solid proof. Okay. And you know, if T1y and T2y are equal, right, and they equal up to mg, essentially each one must therefore be supporting exactly half of the weight of this object. Okay. So with equal angles and with symmetry, T1y will equal T2y. Since they are exactly equal to one another and they sum to mg, they're each taking care of exactly half the load. Does that make sense? So now we can solve this, all right? Now that we've laid all that out, it's fairly solvable. So let's go with this. Let's say T1y, okay, should be exactly equal to half of mg. Can you follow that? Does that make sense? Why the negative? Well, what I guess we're saying is if T1y equals T2y, we could just say it's like T1y plus T1y equals negative mg, or 2 times T1y equals mg, negative mg, or T1y equals negative 1 half mg, or 1 half negative mg, irrelevantly. So we're just essentially doing another mathematical proof, right? Now we can go ahead and solve this. So T1y equals negative 1 half, the mass was 4 kilograms, times negative 9.8 meters per second squared. Oh, was it 10 kgs? Okay, whoops. Thank goodness we caught that one. Okay. So what is half of 98? 49 and a half? And that is in newtons, right? Kilogram meters per second. Distribute that in. T1y must be equal to 49.5 newtons. And I added in an extra half that I did not need to. Sorry about that. There we go, 49 newtons. Once you have that, let's scroll back up and see what we do with it. So we solve for this, 49 newtons in the upward direction. We know these are equal, so 49 newtons in the upward direction here, okay? We know that these angles are all equal, right? Interior angles are equal, interior opposite angles are equal. We should be able to now solve for what our tension is, right? We know that's 40 degrees, we should be able to solve for our tension. So this is the opposite angle, Ft is the hypotenuse, so we should be able to say then that the sine of theta equals opposite over hypotenuse hypotenuse is, of course, tension 1, your tension force 1, or T1 is equal to 49 newtons over the sine of theta, right? And solving for that, T1 equals so I get 76.23 for that. And we'll just round that to 76. Okay? So we figured out this is 76 newtons. Therefore, this has to be 76 newtons. And we're done. We solved the problem of the hanging plant. So there was a question about whether or not we need to add in a direction here. Like, do you have to say the tension is 76 newtons, 40 degrees north of east? Not really. Tension's a little bit different, right? Like, it's not like an airplane where you're going to be like potentially changing your direction that you're traveling at. Usually in a static situation, this just stays put, right? So if I ask something what the tension in a rope is, you're not really going to have to say, besides the fact, I guess, that you're going to have to know that essentially the tension is acting up and to the right here, okay? And the reason why is because it's got a component that goes like this, and it's, right, so that's the x component of it. It's got a component that aims up like this. And if you add them both together, right, the sum has to be from the start of the first to the end of the second, right? So it's got to be up and to the right in terms of which way the tension is pointing, right? In real life, I guess it's hard to kind of say that a tension is pointing in a particular direction, maybe. I don't know. Like, it's just what the tension is in some sort of, rope or cable. But I suppose when you break it down, yeah, it's got to be, you got to consider it to be up and to the right. But you don't have to put in, 40 degrees north of east. You don't have to do that. Okay?